Hello and welcome back. We are going to kick things off now with session 8, Introduction to Practical Machine Learning. Before I pass things over to Lilith, I do want to just go over a couple of administrative items. This session is being recorded. All meeting materials, including slide decks, recordings, any applicable notebooks, will be shared after the sessions conclude. Just a reminder to do please give us a couple days to get those materials turned around to make sure they're 508 accessible. And then there is a Q&A session at the end of our presentation, as long as time allows. Please make sure to put your questions in the Zoom chat so we can have record of them, and then anything that needs further clarification or we may not be able to answer or get to, we can make sure that those get answered and then published as well. So with that, I'm going to be passing things over to Lilith at this time. Thank you.
All right. Thanks, Julia. Do you mind if I take over the screen share here? Okay. Come on. Okay. Can you guys let me know if you see the screen which says Introduction to Practical Machine Learning?
We can.
All right, perfect. All right. Good afternoon, everyone. Hope everyone can hear me okay. Welcome to the session of Introduction to Practical Machine Learning. I'm Lalit Nuklar, staff data scientist with the user services team. And in today's agenda, what I got for you is we're going to talk about what is machine learning, what are the types of machine learning algorithms that you see, and we'll get into more on the practical side of things, which is basically talk about machine learning lifecycle methodology. We talk about what is CRISP-DM, which is cross-industry standard process for data mining. It's been out there for quite some time and has become an industry standard for this one. Whenever you want to do this within the CCSQ environment, you're going to use Databricks. So we're going to show you what the advantages are when it comes to doing machine learning development lifecycle using Databricks. After that whole theory is done, we're going to go walk through the demo. And at the end, I'll take question and answers. So the objective of this is what I'm really hoping that audiences will get familiar with the steps that is involved in implementing an end-to-end machine learning pipeline. That's where you get this raw, messy data and you have a final intelligent data product. Now, there are three key things that are important for that, which is choosing the right data, choosing the right algorithm, and deploying this model so that you get intelligent answers out of it or intelligent outcomes out of it. Before we dive in, I want to make really sure that what's something that's out of scope here is that this is not going to be a treatise on machine learning algorithm, how to develop new algorithms. We are not going to get into the linear algebra that's involved, matrix decompositions, calculus, or statistics, or any of those things. There are far more brilliant people like Andrew and Tom Mitchell who have done really good job of presenting this thing. I have included that in reference section where you can go listen to their videos or read the book that they have written. And they do a far better job of explaining the theory behind it. So with that, what is machine learning? Well, it's a study, a field of study within computer science and AI that concerns with the development and study of statistical algorithms with a goal of teaching them these computers to learn from the data and generalize onto the unseen data without explicitly trying to say, do this, do that, and stuff like that. Now, when you come to machine learning as a student, you're formally given a definition, which is by Tom Mitchell, one of the pioneers in this field, is that a computer program that learns from experiences E with some class of tasks T, with a measure of performance P, where the performance P increases and improves over time on this task as it increases with experience. Now, machine learning and statistics, and I'm hoping a lot of people coming from the statistical background can relate to this. They're closely related, but they're distinct in what their principal end goal is. Statistics helps you draw population inferences from a sample, whereas what machine learning is trying to do is finds generalizable predictive patterns that you can apply to the unseen data that you'll see as you start collecting more. Okay, with that, different types of machine learning algorithms. I wanted to kind of let you guys know what all you'll see when you start working in this field. There's supervised learning algorithm. What that means is you have your raw data, you know what the outcome is out of that data, and then you try to generate models that can actually go through the pattern of this data and help you detect what that outcome is. The outcome is labeled, so it will try to learn from those labels. So think about spam detections that you see in your emails, or cancer detection when you go to a doctor's office and they're looking through the imaging studies and it tells you what it's doing. So stuff like that. It has a large corpus of data that it can go through, learn, and then it applies to them. Then there are regression problems. You go on Zillow, it says, okay, this is this guesstimate of this thing. So that is predicting housing prices, which is a regression problem. When we get to the demo here, I'm going to present to you a supervised classification learning algorithm problem. And we'll walk through that without giving you too much of a spoiler here. That's what we're going to look into. Now, there is the other class, which is the unsupervised learning. When you get to unsupervised, you have absolutely no clue what the outcome is going to look like. So you try to identify patterns, clusters in the data, like customer segmentations or market basket analysis. Anomaly detection is one more thing where you try to look for, like, okay, everything's clustering here, but there is something which is way outside of the outlier. So it kind of helps you with. So unsupervised learning algorithms will help you with that. The third one, which is kind of becoming more popular, in my opinion, is reinforcement learning. It's an agent that will interact with the environment and collect the data on that environment. And through rewards and penalties, will learn how to maximize the long-term success. So if you have ever seen like robots kind of playing soccer and trying to score a goal and all those things, that's where they kind of end up using a lot of machine learning, reinforcement learning. Penalty when the ball goes out, you get points or incentives when you score, and then the robot agent will learn what it's supposed to do. A long time ago, DeepMind's AlphaGo is one of those things which actually defeated a human Go champion because of what they used as neural networks and reinforcement learning algorithm. That said, you have three main goals with machine learning algorithms. Excuse me. Descriptive, which is, I got this large data. What's going on? Patterns. Let me know. That's descriptive. Predictive. You want to predict based on what you're seeing in the data. The end goal of the machine learning algorithm is going to tell you that this is what is going to happen next if you see this kind of a data set, or this kind of record comes in, this is what it's going to look like. Prescriptive, telling you what to do. Based on the data and the patterns that it has observed, it can give you what is the future course of action that you can take. So with all of these, what ends up happening? We get into what you call as the practical machine learning. This is more of the applied nature of the machine learning. What you're doing here is developing, quote unquote, intelligent data products. Now, what I mean by that is, when you're developing intelligent data products, you're dealing with real world data. The real world data is going to be messy. So you need to prepare your data. You need to tune the models that will actually work on this data. And then you are actually going to deploy this in real time, and it is going to interact with the data that's coming in, either as a batch or real time or whatnot. Now, once you get into the practical aspect, there's a lot going on with this thing. For a successful end-to-end machine learning project, there are multiple personas that are involved. What I mean by that is that they're going to have a product owner or a lead who has to determine what the scope of this data product is going to be. Data engineers who are trying to help you gather all the data that is necessary to be able to analyze it and run the algorithm. Data analysts who are looking at the data, kind of coming up with, like, okay, whether the data looks good, is there anything else that need to be done with this data, kind of giving you those initial reports of this is what the the ingested data looks like. Then data scientists are the one who can take this data, clean it, model it, say that, okay, this model looks good, we can use this on this data, and then you have DevOps or ML engineers who can go in and put this model in production, so that, and then determine on how to be able to do the one of these three goals that we talked about on the real world, in production. Now, when I say personas, multiple people can do this thing, but these are kind of different hats that someone have to have when they're doing an end-to-end machine learning project. Now, with all of this going on and different skills needed to do an end-to-end machine learning pipeline and a practical machine learning, so you need to have a standardized process, this is an industry standard process called CRISP-DM, stands for Cross-Industry Standard Process for Data Mining. It's a widely used machine learning lifecycle methodology, and they break down this entire process into 6 phases, which is business understanding. You need to understand what data product you're building. Then once you know,
Didn't seem to be okay last night, when we were watching TV.
I'm sorry. All right, so business understanding, defining the objective and the success criteria of what this data product is going to look like. Then once that is done, you need to go collect the data and explore the data. Say, okay, what do we have at our hand? Can we even do what is being asked of? Preparation, kind of cleaning the data, transforming it so that the machine learning algorithm can actually do a successful modeling, which is where the modeling phase comes in. You train the model, test it, pick the best model, and say that, yep, this is what I'm going to use. Evaluating it is basically tied into it, assess the performance, impact, so on and so forth, and then deploying it. Take the best model, put it into production, and then it will start doing what it's intended to do. Now, CRISP-DM is basically a very iterative process. It's not like you go as a waterfall. Once you're, so it you kind of go back and forth between each phases to finally, when you get to this deployment phase, when you put it into production. This notebook is going to be available to everyone. There is always this thing where what is required of each phase and what's going into each phase and what's going to come out of this phase. I have all of them, and I'm going to walk through at a very high level in my demo through this process. Now, CRISP-DM actually works really well with Databricks when you're trying to build your end-to-end machine learning projects. And the reason for that is, first of all, Databricks, you must have heard this a million times. It's a unified platform for machine learning. It integrates data engineering, data science, all of these things together seamlessly into one platform. Well, what that actually means is you can start training your machine learning algorithms on a large data set. More data, better performance. So the scalability that comes with Databricks is really helpful in building really good machine learning models. Collaborations. You have this notebook environment. As you can see, a lot of people have already came into this notebook. It helps you to collaborate easily with your teammates when you start building this pipeline. Everything is built off of Delta Lake, which means it gives you this reliable, scalable data storage where you can start storing all your ML artifacts, the raw data, the clean data, the gold standard data, the features that you want to use. Everything can be stored at central location for people to start using it even at a later stage. There's something called ML flow integration. I'm going to show what that is when we go through the demo. It basically simplifies your model training and tracking. One thing I'm going to impress here is that in the practical machine learning, the machine learning models are democratized. You don't have to do anything. A lot of these things will come out of the box. You can start using them. But once you're using them, what exactly are you is the best model to use? Those tracking can be cumbersome if you do it manually. ML flow helps you do that in a very nice manner, which I'm going to show as part of my demo. Then there is the MLOps support. Integrating it with CI/CD pipelines, you can streamline the deployment of these models, and it can start working on your data easily. There are a lot of additional features that are part of Databricks. And when you go through the Databricks documentation, you can see all of these things. This is not yet supported in our current implementation of Databricks. It's going to come at some point in time, but till then, we can still do a very successful end-to-end machine learning with whatever we have. All right. With all that said, let's get into the demo. Now, to put this into practice, what I've done is took a use case. And the use case that I have is that I took what is called a real-world evidence data. Now, what that means is that it's clinical data, which helps you analyze, understand the risks or benefits of a medical product. What I mean by medical product is you want to see whether a drug is working fine in the real world population, or a device like your stents and all of those things working in the real world population, or a process that you have put in place as for an intervention. Is that working properly? A lot of times when these drugs or these processes hit the market, they go through a controlled clinical trials. But once that is done, how it does in this wider population, this is how you'd look at it. You do real world evidence analysis off of that. So in order to do that, let's start with the cluster configuration that we have. Give me 1 second. Let me get this one started. Okay. Now I'm starting out with my compute cluster here. As it's warming up, I'm going to tell you what that configuration looks like. It's a personal compute, standard run-of-the-mill. I don't have to use anything fancy for what I have here. Just with one driver, it will scale up to 30 workers if I need it. Standard 14.3 Databricks runtime is what I have. But that is the cluster which is starting up. It's my personal compute clusters, which, as we heard earlier, that's what we are actually moving towards, using this personal computes rather than general purpose clusters. The reason I'm bringing this up is that almost all the time, this will work for you. All right, with all of that said, what is it that we are trying to achieve here? The one thing that we are trying to achieve here is predict cardiovascular disease. So let's say your business stakeholders come to your analytics team and say that, hey, you have access to EHR, claims, pharmacy data, outcomes data. Can you predict the likelihood of cardiovascular disease based on certain measurable risk factors? Now, why would someone want to do that? If you can predict cardiovascular disease in patients that are coming for checkups, you can inform the patients of the risk, mitigate hospitalizations, improve their quality of life, and help overall reduce the cost of treating these patients. So this is how you're building that intelligent data product using machine learning algorithms. So you need to have what your end goal is and where you're going to start from. Now, Databricks has this freely available data set here in RWE EHR. If I'm not mistaken, it has all of these here: allergies, care plans, conditions, encounters, imaging studies. You can do a whole lot of other things with this data, by the way. Most of the times, the way you are going to start it is that, okay, this is the problem that they want us to solve. Let's go get the data. And this can be out on your S3 buckets or on your UFM somewhere sitting out there. You can go grab that. And in here, it's my CSV files that I have sitting out in this workspace location. So, okay, then the first thing that you're going to do is ingest this data. And I simply iterate through all of that files and put it into my catalog, database catalog, which I'm going to show you here in a minute, which is right here. So anything that does not have this _silver suffix is everything that's been ingested using this set of code. And in here, I have readings from CSV and doing it. You can have it reading Parquet, JSON, all of these things. So once you have access to this, you can use it and read it. Once you read in the data and you create your database tables out there, then you have collected what you think or you believe is the data necessary to solve this problem. Now, the next step is understanding this data. Now, this is where things actually start getting interesting. Well, you have now you collected the data. All right, you want to figure out what's going on with this data. So the tabular format of this data looks like this. You got ID, birth date, death date, all of these things here. Let me scroll to the right location. Sorry about that. Yeah, so you have everything about this page, about this population listed here. Now, you can click here, click on the visualization and build your dashboards to look at this data, which is basically a very high-level exploratory data analysis that you need to do to basically figure out what's going on with this data. Is it even useful? So you look at this gender distribution. Okay. It's pretty fairly well-balanced data based on female and male. Okay. Or you might want to look at everything that's available. So to look at everything, this is a nice little feature that Databricks has, which, a side note, up until like 12 to 18 months ago, you had to write a lot of code to just build this data profile. But here you can click this button here and build and just profile this entire data. I'm going to click expand here and it will start showing you. This is ID, but death date is missing about 85% of the data. It's okay. Well, that means people are alive, so we're not going to worry about it. But if there is anything that is important as a feature and needs data, and it is missing, this is a stopping point. You stop here and say that, yep, we need this particular data, but we see that it's about more than 50% nulls. I can't use this data. Then you get into what needs to be done after that. It actually helps you build nice little graphs here, like male and female. Oh, this is marital status. I'm sorry, like race. If that is an important factor for any model that you're building, you can look at the distribution and say, all right, is it skewing one way or the other? Things like that. Similarly, I've done that for condition encounters, and you'll have something similar, right? Like encounter class, it's ambulatory versus, a wellness visit, inpatient, outpatient, all of these things. So you see, this actually helps you look at the data and basically decide whether it is usable or not. I do this for conditions, encounters, and all. This is where I change it to SQL. You can write straight up SQL and do this particular exploratory data analysis. Once you see this data, once everything looks okay here, you move on to the next step, data preparation. Now, we just saw all of this data. It's fairly clean, not a lot of missing values and all of those things for the key data points that we may be interested in. But all of this has got imported as strings, even like the start date, end dates, birth dates, all are imported as strings. So computations will become difficult. So we need to fix the data type. Then you need to do your data selection. What is it that you want to include as part of your criteria cohort and what you want to exclude? And then you create that. And then feature engineering. So all of that will happen in step 2. One thing to know here is this is important. The step 1 of gathering your data and understanding the data and preparing the data. Practical machine learning, if you are in that realm, your 70 to 80% of your time is going to be spent here. This is absolutely crucial to be able to do these 2 steps, right? Take as much time as you want to do this thing correctly. All right, that said, we will fix the data types and I create the silver tables and you want to follow the medallion architecture to just make sure that you're cleaning the data at each stage and everything. And I cleaned up, like converted whatever the date columns are. I convert the date columns here and loaded them up into the silver tables. So just if you want to know, say start and stop are strings here in this thing. If we go back, look at the silver, I converted them to date. This is just an example. You might have to do a lot more than what I'm showing here, but this is the stage where you do that and get your data ready. Next step, and this is where It's very important to spend as much time as you can. And this is what I think is the crux of practical machine learning or applied machine learning is feature engineering. I know it's a fancy term, but what it really means is making sure you transform your data so that you can run the model of your choice on that data. And like, and it could include very simple examples of feature engineering or very complex. Like you got birth date and death date, computing age, that's a feature you need, and that's feature engineering, as simple as that. You have only height and weight of the person, you have to compute BMI. Again, if BMI is the one that you want to use, that's a feature that you are engineering out of the data that's available. Now, these things are so innate in our mind that we don't think about it, but these are actually feature engineering. So all these kind of transformations that you have to do, there are different kinds of them. Like you have binning, like you have numerical data. Let's say you have age, and you can use age as a number for a lot of these things, but like for market segmentations and all those things, you want to divide this. So 18 to 25 is one bin, 26 to 35 is another bin. So binning, converting the numerical data into categorical variable, that's another, it's a transformation, it's feature engineering. And there's a fancy term called one-hot encoding, but that's basically saying, oh, I got male and female as gender, but that string models cannot do well with strings, so I'll convert them into numbers, change it to 1 and 0. That's basically what one-hot encoding is. Feature extractions and selections. I mean, this is, as I said, choosing the right subset variable, and I'm going to get into more of what feature selections actually mean in a little bit here. But yeah, creating a new dimension out of your existing data, like BMI or age as a number. These are the ones that you have to do and introduce this into your model so that the models perform better. Then this is another important thing, and a lot of people don't usually think about it unless you have experience with it, is feature scaling. Now, in our case, I'm going to use age, glucose, systolic, and diastolic. Each one of it have different range, which means they have different numbers, which corresponds whether these are significant or normal. Having those numbers, the algorithms don't understand what those numbers are going to do. It's basically it's just reading through the data. Now, if you scale them to one single scale, it makes the models perform better. So you have min-max scaling where you scale all these features so that they fall within same values. Like in this case, 0 to 1. All the values will be between 0 to 1 for each feature. That's scaling. Then there is z-score scaling. Doing this, you are basically taking all the numerical features and bringing them down to the same scale so that models will know what to do with it properly. It improves the accuracy of the models that you're going to build. With all of this, we go on and build our cohort. Now, in our case, for the CVD risk cohort, I have it as a separate SQL query. Very simple. I just took this thing. What is this one? Systolic. I went ahead, grabbed whatever the systolic value is, diastolic, height, weight, cholesterol, glucose, whether they're smoking. And we are going to use cardiac as with these codes, we'll say whether whether the patient has CVD or not. And using all of that, I build out my cohort. What I did as an exclusion criteria is make sure that all the patients are adults and about 21, not adults, but about 21. The thing is, less than 21, their heart will be relatively healthy and it can imbalance my class. So about 21, we build the cohort here. Now with all this data available here, let's go back to our notebook. Once the cohort is created, and I have listed the paper that I used to get these features, if somebody is interested to look at it. We have our cohort ready. There's a section about feature selections. There are different methods that you use. I just used, in my case, you'll see a built correlation coefficient so that you'll understand what these mod data is doing. And we're going to talk about wrapper methods. I don't end up using so much, but it's basically taking each subset of features and try to add them into the model enough that you know what the right model is going to look like. Or you have start with 150 features and start trimming down to finally a very small subset that actually does perform well, and the model will perform well. Then the last one, and the embedded methods. And I'm going to talk about random forest and gradient boosting because these get embedded within the machine learning algorithm itself so that it's doing your feature selection as it's building the models. There are other feature selection techniques, which is principal component analysis, and linear discriminant analysis. These are dimensionality reduction techniques or features reduction techniques, which basically distills it down to the important components from the wide data set that you throw at it. Now, with all of these feature selection criteria and feature engineering done, we get into modeling, the fun part. Once the cohort is ready, we have to determine what kind of algorithm we are going to run on this one. Most of the times you're going to deal either with supervised or unsupervised. Even with unsupervised, unless you're doing clustering techniques, you don't have to worry about it. Classical machine learning or practical machine and for all practical purposes, you'll end up sticking with classification or regression supervised learning. In this one, since our CVD risk is either 1 or a 0, it's a classification problem for us. So given our cohort, given the data, how are we going to build the model? So Spark, which is what Databricks is actually built on, has its own native machine learning library. You don't have to do any install or anything. You can start using it right out of the box here. I have this hyperlink. It's spyspark.ml. It has all the common learning algorithms that you will need. You can do featureizations. I mean, as you're building the model, you can actually throw in more feature selections and scale. And I'm going to show how I'm doing that one here. Helps you build the pipelines because once you have the data, you are going to do a lot of transformations, and each of the transformation is a particular stage in that pipeline. So it helps you build the pipeline so that you can reproduce that at a later stage. Persistence, you can save all of those models and algorithms, including the pipeline, so that when the new data comes in, all you can say that, oh, this saved pipeline, applied on this one, because I know it's the same kind of data. And there are other utilities in there for data handling, doing other statistics like correlation coefficients and all those things. All of that is included in the Spark ML library. Before we do the Spark ML library, this is one step that you have to do. You have to install ML Flow and restart Python so that it takes up, and then import ML Flow and start on Autolog. I'm going to show you in a minute why you need to do that. Well, with that said, I'm going to load in our cohort that we just saw. And the data actually looks like this. You got age, gender, systolic, diastolic, height, weight, cholesterol, glucose, and CVD risk. Again, there's a subset of the data that's needed to do CVD. I'm pretty sure there are a few hundred variables that you can put in to do a proper CVD risk analysis, but we'll start with that. The first thing I want to do is take a look at this data and see how each of these features are correlated against each other. So build a correlation matrix. So as you see here, all of these come from the PySpark ML or the Spark ML library that I was talking about. Now, before we get in further, what we do here is, all right, as we talked about, gender is male or female, so you want to index it. And you want to all the data has to be vectorized within the Spark ML library so that it can get distributed. And I'm going to show you how it actually looks, but it helps in doing distributed processing. You have sometimes you might end up using petabyte scale data with different clusters. If you can vectorize this data properly, you could still be able to churn through all of that data. And then you got once we have assembled all of that, what we do is we'll build the correlation matrix and see how it looks like. All right, here it is. All right. Oh, this is as we know, systolic and diastolic are highly correlated, but we are interested in our CVD. So CVD, as you see, the features, and again, since I used the paper to go through this, so I kind of cheated a little bit and knew what features to use. But this will usually help you figure out, picking out the actual features that if they are uncorrelated with the CVD, you can use that to build a model. Sometimes the classification problems will need weak correlation or uncorrelated variables, features to build a model. So as we see here, none of our independent features, which is all of these age, gender, and all of these are independent features, are highly correlated with our target variable, which is the cardiovascular disease or the output. All right, so now since this matrix looks okay, we don't have to do anything else. We'll pick which algorithm to use here. The usual suspects are your logistic regression, random forest classifier, and GBT classifier, which is the gradient boosted tree classifier. Logistic regressions are very easy to understand, and they're simple, but they're highly effective. So a lot of people start with logistic regression for a classification problem with a cutoff of 0.5. It's a probabilistic way of determining whether you have yes or no for the output, or in this case, whether there's a CVD risk or there's not. Then random forest classifier is basically it's collection of various decision trees. You do random forest to avoid overfitting. You don't want the algorithms to learn too much from the data that's presented. It needs to generalize so that it can actually perform admirably on the unseen data as well. So random forest classifier actually helps solve that particular issue. Gradient boosted classifiers is another one. These terms, random forest and gradient boosting, if you remember, we actually saw that in feature selection as well. So these are the way you take your standard decision tree, which is again a classifier, but by adding random forest methodology of feature selection or gradient boosting of methodology of feature selecting, you are basically bumping up the evaluation metric or the accuracy or the success criteria of these algorithms. All right, so we are going to focus on these three. There are other classification algorithms. Decision trees is one, which is your standard tree if else kind of thing that you do. Then there's multi-layer perceptron. This is basically a neural network, which is kind of geared towards building for classification data. If your data relationships are nonlinear, MLP, multi-layer perceptron, are the best way to go. If you have a highly dimensional data, then support vector machines actually do a decent job at getting you what they call as the hyperplane, separating your outcomes. Do that. Then there is naive Bayes and factorization machine. The factorization machine is kind of used more in your click predictions or item recommendations. Think about Amazon recommending you different items. One of the algorithms that they will end up using is the factorization machine algorithm. Does really well with high dimensional sparse data. So all of these are actually available to be used right out of the box with Spark ML. Then the next thing we are going to do is test train split. Now, the reason why you have the cohort here, let's say you got 1,000 rows, and it's small, but just as an example, you don't want your machine learning model to learn everything from that 1,000 rows, which then you get into like overfitting, biases get introduced and all of those things. You don't want that. So in order to avoid that, you take your 1,000 rows data set and split it into, let's say, 70-30. 70% is going to be used to train your model, And once the model is trained, it's going to be tested on this 30% of the data that you kept on the side, so that it actually be, it kind of helps you evaluate your error on this unseen data, which is part of your original cohort, but gives you a better real assessment of how much of generalization will happen with this model that you just built. We'll see the evaluation metrics and all of those things, but it's essentially trying to make sure that, there's no bias. And when a new data is introduced and the machine learning, this algorithm has to do its job, it is doing it properly and not, giving you an error because it overfitted on the data that it learned from. So that said, this is where we get started. I got logistic regression here that I kind of get it from the classification package module, random forest classifier, GPT classifier, and decision tree classifier. Again, you got this pipeline here. I have my columns list here. I know that the gender has to be indexed. So there is something called string indexer that will actually index the data for you. That is basically, encoding it into ones and zeros. Then you assemble the vector. We talked about scaling. So that standard scaler, it's right out of the package. You get this, you say that these are my inputs as a vector. Give me the scaled features, standard deviation. And then there's the logistic regression. What are you building the logistic regression on? Scaled features and what your label is. With all of that done, you build your pipeline and you say, what are my stages? All right, when you get a data, do the gender indexing first, assemble the vectors, scale that vector data, and then apply the logistic regression model. And that is going to be what my pipeline is going to look like. Once you have that one ready, you take your cohort, and this is where I did this train test split of 70-30, the one that I was talking about. And once the pipeline is ready, once your cohort data is split into training and the testing data, you just call pipeline.fit. Fit the model on the train data, and you get your output here. And then you make the prediction on the test data. It's as simple as that. Once you know what you need to do with your machine learning algorithm, it's just these no more than 15, 20 lines of code that you need to get your model out. Then after that, you do still have, if you want, you can start doing your evaluation here. This is binary evaluation. So we look at the ROC curve. We look at the error, which is 1 minus accuracy. And then you look at your F1 score. Remember the ML flow thing that we did? Databricks has this whole thing integrated here within what they call as the experiments section of the machine learning playground. And that will log your run. I'm going to show you that in 1 second here. So once that is done, and this is how it's going to look like. It has this vector, it has your data, and it has your predictions here. This is what the output looks like from this little thing, the display that we did from the predictions. Similarly, that we ran logistic regression, we run the decision tree classifier. Similarly, you got everything set up. Already I set up the gender indexes, the assembler, and the scaler. All I have to do is change the pipeline to use decision tree classifier. Everything goes the same. You do the test and train split, and then apply that, and that run also gets logged because we have the auto logger from MLflow turned on. Last two, random, we run the random forest. Again, same way. Honestly, I just copy pasted and just changed the machine learning model that I had to use. It is that easy to do it. And then you got the GPT model run. All right. Now that we ran about 4 models, we need to pick which one is the best model that we can use on this data to predict our cardiovascular disease risk. Remember, I showed you that there's the experiments tab that looks like this. This is where it will have all of your runs. I just did this for the last 24 hours. I've ran it many times. All of your runs get stored here. Just for your understanding, it will start storing all of the runs here within that particular within the confines of this experiment notebook. All right, let's go back to the last 24 hours. So these are the ones that I'm running. Okay, you can look at it as a graph. If you see here, and I'm sorry, this one is a little, I had to make the screen look big so that you guys can see what I'm doing. But this is the accuracy, ROC, and F1 test. As you can see, the ROC for this one is very low. So this might not perform really well. Okay, so which one is that? So if I click on this one, it shows this. If you go here, so that is, and it will tell you here, it's a decision tree classifier. All right, so we know that the decision tree classifier is not doing well because it has a low ROC curve. Then what about this one here? It has a good accuracy. ROC is also pretty much up there, and its F1 score is also high, very high. So this model seems to be the right model that we want to use for our data set for this model to go into production. So what I'm going to do is look at what that model is. Click here. See, it's a GBT classifier. Now you see all of these things, the samplings and the validation, and there's a lot of things that you can change to tune this model to work better. What I did in this case as part of my demo is to just run them on the default setting. But if you go into its API and look at the function call, you can change what the learning rate is and all of those things. So, and coming back to this, given that this GBT classifier that we ran, the gradient boosted tree classifier that we ran, runs the best, what we are going to do is pretty simply, once we have looked at this experimentation tabs here, we know which ones to pick. All I'm going to say is take my GBT model, write it out to whatever location is available to you. In my case, it's this S3 location here on the workbench. And I just save it as just as the CVD champion model. That's a standard term that people use here. Calling it as a champion model is the one that's, you say that this is the model to be used. Okay, so this model is ready now. And then how do you deploy this? I've done this in this notebook, but you can have a different notebook sitting as part of a job, which runs as a trigger or on an interval, but you can just load that entire pipeline into a pipeline model.
Hey, Lilith, sorry to interrupt. I did just want to give you a quick 2-minute warning.
Yep, I am almost done, by the way. This is my last section.
Sounds good. Thank you.
Yeah. So you take the model that you've already stored, load it into, and by the way, when I say a model, it's the entire pipeline that we talked about. You load that into a pipeline model variable, read in the data that you want to predict this data on, and just say transform, and you have your predictions ready. And it's going to start looking like this. Okay, this is the data that I read. And you can also see what feature vector it built, how it scaled, predictions, probabilities that it built, and what is the output is going to look like. And that's it. That's how you take the data, prepare it, build new features, run your models, run different kinds of models, look at its accuracy, look at its other metrics, determine what model works the best for your use case, save it out into the location that you have, and you can run it in just read it in, run it as either in real time, trigger based, or ad hoc basis, and you will have what is an end-to-end successful machine learning pipeline to build your intelligent data product. So in conclusion, you saw what this implementation is. The key is having the right data is important. Feature engineering is the most important step in the applied ML space. Always remember, garbage in, garbage out. If you don't have the right data, you don't expect the model to do wonders for you. That is it. Questions and answers, let me know. And I have some references here that you can go in and take a look at. Thanks, Julia. I can stop sharing my screen.
Thanks so much. I'm not seeing any questions at this time, but while I take over sharing again, we can just give it one more minute.
Maybe I went too fast.
Okay, I'll keep an eye on the chat as well. Okay, I'm not seeing anything. So I think we're okay to go ahead and wrap up. Dan said they're just in all on absorbing the content. So thank you so much for the great presentation. And our next one will be up at 4 p.m., which is CCSQ Quick Site Essentials, which will be our last session for Data Camp. And then just a reminder that around 4:50-ish, depending on timing, we are going to have a closing kind of message from Katie Holmes. So please make sure to attend that and meet us back here at 4 p.m. so we can start things back off. Thank you so much, everyone.